Oh my! There's plants everywhere! Miss Brousseau, come here! Look at all these plants everywhere!
Oh my God, Miss Robinson, you're right. Over there.
We're
surrounded by plants.
So many plants.
Oh my God.
Evelyn and Jamie.
Girls.
Evelyn and Jamie. Girls. Evelyn and Jamie.
Girls.
Science rules.
Evelyn and Jamie.
Girls.
Inertia is a property of matter.
Girls.
T minus 7 seconds.
Evelyn and Jamie.
Girls. Hi, I'm botanist Jamie.
And I'm botanist Evelyn.
We are botanists.
And we study plants. The first ingredient is a chloroplast.
I'll go call my assistant to get one.
Look, I found a chloroplast. I'm gonna go bring it to Evelyn and Jamie.
The second ingredient after the chloroplast is the water. I'm going to pour it into the thylakoid.
And the third ingredient is CO2. So I just have a bag and I'm just going to put it right in. Now we're going to put it into the oven.
In the oven, the chloroplast organelle will be struck by photons of light. While we wait, let's go learn about the light-dependent reactions.
What is photosynthesis?
The equation for photosynthesis is carbon dioxide plus water plus energy, which comes from the photons of light, which produces glucose and oxygen.
Photosynthesis occurs in the chloroplast.
Light-independent reactions occur in the fluid-filled stroma.
The light-dependent reactions occur in thylakoids that make up a granum.
When the photon of light hits the photosystem, this causes an electron to become excited, which causes the oxidation of the chlorophyll A molecule. This oxidation allows for photolysis to occur and water to split into hydrogen ions and oxygen ions and electrons.
Oxygen is a waste product and will diffuse through the stomata. In the diagram, light is striking photosystem 2, which contains a pigment called P680.
P680 is a chlorophyll A molecule that is located in photosystem 2. It best absorbs light of 680 nanometers. When the P680 special pair of chlorophyll A in photosystem 2 absorbs energy, it enters an excited state. Excited P680 is a good electron acceptor, and it can transfer electrons to the primary electron acceptor.
Now the electrons will move through a series of proteins called the electron transport chain. At every step from photosystem 1 to photosystem 2, the energy level is reduced.
In the electron transport chain, the electrons start at photosystem 2, and then they go to PQ, and then they go to cytochrome BC, then they go to PC, the mobile carrier, and then the electrons go to photosystem 1.
When the B6F complex becomes energized by an electrons, hydrogen ions will be diffused into the thylakoid. Now the electrons reach photosystem 1.
Photosystem 1 and photosystem 2 are very similar as they both excite electrons, except photosystem 1 has a pigment of P700 instead of P680.
The electron that just got energized again will move on to ferredoxin.
Then to the enzyme NADP reductase.
This enzyme will reduce NADP plus to NADPH, which is needed for the Calvin cycle, acting as an electron carrier. Specifically, what ferredoxin is doing is donating a hydrogen ion and 2 electrons to NADPH, which is going to go into the Calvin cycle, and the carrier will donate the hydrogen ion and the 2 electrons.
After the Calvin cycle, the NADP will be reduced again.
Now we will use the proton gradient formed from photolysis in the complexes to form ATP.
Now inside the thylakoid there is a strong positive charge. In a process called chemiosmosis, the protons want to move down their electrochemical gradient. To achieve equilibrium, the protons will pass through a protein called ATP synthase.
This recharges ADP to ATP by connecting a molecule of inorganic phosphate, which is called phosphorylation.
You may think we are now done, but this process will continue making NADPH and ATP.
The cyclic process of the light-dependent reactions happens because more H plus ions are needed for the Calvin cycle and more ATP is needed to fuel the Calvin cycle than NADPH is needed. So the cyclic process happens, so the H plus ions are produced, so ATP can be produced for the Calvin cycle.
In the cyclic cycle, the electron will travel in a different way. So it will go from PQ to B6F complex to PC to photosystem 1, then ferredoxin, then back to PQ, and it will cycle around. ATP is created the same way as we mentioned before in the past cycle, but the electrochemical gradient is coming from hydrogen ions diffusing through PQ instead.
Oh my god, it's ready, let's check. So first it formed glucose, a 6-carbon sugar,
And we produced oxygen.
as a byproduct,
I hope you will enjoy breathing the oxygen that you have created.
and eating the glucose.
Tell me pretty lies, look me in the face. Tell me that you love me.